All right, let's just jump right in. Sometimes advanced math can feel, well, super abstract, right? But if you really look at it, it's actually this incredible quest. It's a search for the basic rules that make everything tick, from the whole universe down to the tiniest quantum particles. And today, we're going to join one of those quests, a quest for stability that's hidden inside some really fascinating equations.
So our guide for this whole thing is a paper by Bassas and his colleagues, and you can see right there in their abstract they are laser focused on something they call ground state solutions. What that really means is they're trying to figure out if a super complex system can even have a natural stable state. And if it does, what does it look like?
Here's how we're going to break it all down. First, we'll try to get our heads around the equations themselves. Then, we'll get into the main event, the search for these stable ground states. We'll find out there's this critical tipping point that acts like a light switch for whether they exist at all. Then, and this is cool, we'll see that there can be more than one right answer. And finally, we'll pull it all together and see what the shape of the answer really tells us.
Okay, first up, equations of the unknown. Look, before we can find any answers, we got to understand the questions. And in math, the questions are always wrapped up inside the equations.
So the heart of this whole system is something called the fractional P-Laplace operator. I know it sounds like a mouthful, but the idea is actually pretty intuitive. It's basically just a way to talk about systems where things don't just affect their immediate neighbors. So forget about billiard balls just bumping into each other. Think more like dropping a pebble in a pond and watching the ripples spread all the way across. That's the kind of long-distance interaction this thing is built to describe.
The researchers kick things off with what they call the homogeneous system, or just pH. The easiest way to think about this is that it's the simplest, purest version of their model. It's like the basic blueprint, you know? And their first job is to figure out its most fundamental, most stable state.
And that leads us perfectly into our second section, the quest for ground states. This is really the heart of the paper. It's all about finding a system's favorite state, its most natural way of being. So this big question, what in the world is a ground state solution? Well, think of it like this. It's the most stable, lowest energy state a system can be in. The analogy here is perfect. Imagine a ball rolling around on some hills. The ground state is that moment when the ball finally comes to rest at the very bottom of the deepest valley. It's found its natural, lazy resting place. It literally can't go any lower. That's the prize these researchers are after.
And this brings us to the first huge question they're trying to answer. For this particular system they're looking at, do these stable ground states even exist? I mean, is there always a valley for that ball to settle into? Or could it be that sometimes a system is just fundamentally restless?
And that brings us to section 3, because the answer, as it turns out, isn't a simple yes or no. It actually all hinges on a single tipping point, a kind of on-off switch for stability itself.
This is one of the paper's first big breakthroughs. It all boils down to one little number in their equation, an exponent they call Q. If Q is less than a certain magic number, that's the subcritical case, then bingo, a stable ground state exists. The system can find its peace. But if Q hits that critical number exactly, the switch gets flipped. Suddenly, no ground state solution exists. The whole system is just too unstable to settle down. So we know that a stable state can exist. But here's where it gets really interesting. Is there only one? This question opens up a whole new layer, a multiplicity of solutions. Or, put another way, just how many different ways can this thing be stable?
To figure this out, the researchers pull out a really cool tool from a field called topology. It's got a wild name, the Illustronic-Schnirelmann category, but don't worry about that. All you really need to know is that it's a way to put a number on how complex a shape is. For example, a plain old flat disk is pretty simple, but a donut shape with that hole in the middle, that's considered more complex.
So why do we care about the complexity of a shape? Well, this is the mind-blowing part, and it's what the paper's Theorem 2 is all about. It turns out there's a direct connection between the shape of the space the problem is happening in and the number of stable solutions you can find. It's incredible. The more complex a shape, the more stable states it can actually support.
And the paper gives us this fantastic example to make it all click. Let's say your space is just a simple disk. Its complexity score, that LS category, is just 1. Okay, doesn't tell us a whole lot. But what if the space is shaped like a donut, an annulus? Suddenly its complexity score jumps to 2. And here's the kicker. Because of that hole in the middle, the math guarantees that you're going to have at least 2 totally different stable solutions. It's wild, right? The actual shape of the space is telling the system how it's allowed to behave. Which brings us to our last stop, the shape of an answer. Let's pull the camera back for a second and think about what this all really means.
At the end of the day, the big takeaway here isn't just about this one set of equations. It's about developing brand new ways of thinking. It's about understanding a truly deep principle, that these abstract ideas, things like the shape of a space, can have very real, very powerful effects on how a system can actually exist and behave.
And that kind of leaves us with one final big question to chew on. If math really is the language the universe is written in, this kind of work is a huge reminder of how much of that book we still haven't read. It just makes you wonder, what other amazing, fundamental secrets about our world are out there, just waiting for someone to find the right language to describe them?